Thank you for tuning in. Hello and welcome to today's webinar, where we want to take a closer look at our recent release, CAESES 5. My name is Matthias Brenner. I will be your host and moderator today. I'm currently responsible for sales and friendship systems, and before that I worked several years in pre-sales and engineering here in the company, where I've been for about 13 years now, and I'm a naval architect originally. I'm joined by a few of my colleagues from our support department. The first one in order of appearance in today's webinar is Carsten Fütterer. He's a CAE applications engineer here. He's specialized specifically on powertrain and turbomachinery applications, and he's been with us for about 8 years. Originally, he's a process engineering Master of Science. And I'm also joined by Hedi Böttcher, another colleague from the support department and also marketing manager here at Friendship Systems. She joined us not that long ago, about 2 years ago, and she worked on her master's thesis here at Friendship Systems on a topic that we will also see later on today. And she's an engineering science master. And my third colleague here today is Heinrich von Sado. He's also an engineering science master, support engineer here at Friendship Systems, and he's specifically focused on maritime applications, so ship hull design, propeller design, and things like that, and he's been with us for almost 4 years. So plenty of experienced colleagues that will show you the news in our new release in more depth in a live demos today, and I will guide you through what is new. Before we start with that, I have just a few housekeeping issues. The webinar today will be recorded and then will be available for replay on our website or YouTube later on, but also with the link that you will receive tomorrow. After this webinar, you will have access to the recording. If you have any questions, we want to do a quick Q&A at the end, as much as time permits. So you have the possibility to enter your questions in the GoToWebinar panel, and we'll try to address all of them or as many as possible during the Q&A session. Also, as a small preliminary announcement, we're planning to do some additional webinars later on that might go into even more detail about some specific topics. And which topics we want to cover in those webinars is still open, so we would like you to give us your input in a short survey that will pop up at the end of the webinar or when you leave the webinar. So the survey is very short, might take just one minute, so please give us your input there. That would be highly appreciated. So before we get started with CAESES 5, the new release, most of the people maybe that join us today are familiar with our platform CAESES, but for the ones that aren't, I want to give a quick introduction. What is CAESES? Basically, CAESES is a platform for simulation-driven design of geometries, components from different applications, from marine applications, turbomachinery, powertrain, other flow-related applications. And basically, as you can see in this overview here, CAESES is composed of 3 components. The first one is a CAD environment. This is a very specialized CAD environment with a strong focus on the variation of the geometry and specifically of complex geometries that have often free-formed shapes that are typically not so easy to parameterize with other tools, and especially not so easy to vary in a robust way. So this is our main focus: vary the geometry so that all the variants that need to be created are done in a robust way. but also to parameterize these geometries in an efficient way, which means that we have a high degree of flexibility, but as few parameters as possible, and also provide these geometries in a simulation-ready state, which brings us to the next component, which is what is called automation here. And what is meant by that is the interfacing of cases to external computation tools, flow simulation, structural simulations, or other types of computations that are done with input provided by cases, geometry input, other input values and files, and these external tools provide the feedback about certain properties of the geometry that might be the measures of interest for our optimization, which brings us to the third and final component of CAESES, which is the optimization environment, where we can take our parametric CAD model that we can change and vary in a robust way, and the results of the external computations for these variants, and we can run design studies or optimization runs, and this environment provides all the necessary algorithms, but also tools for post-processing and looking at the results and organizing all the data that is created. So this is just a quick glimpse at what CAESES is for the ones that are not familiar. So now let's take a look at our new release, CAESES 5. And as I say here, CAESES 5 can be regarded as a beginning of a new generation in terms of the development of CAESES, and it brings along news in terms of technology, so basically what's under the hood of CAESES, but also what is on the outside, which means the user experience, the things that you will readily see when you work with CAESES and open it. And in terms of the things that are happening under the hood, but also some of the things that are directly visible, this release is a new platform in which many years of development went into, and this is the new platform upon which also following versions of CAESES will build, and creates the necessary foundation also for many future developments that we have already on our roadmap or that will come on our roadmap. So yeah, come along and let's take a look at what's new. So the highlights are a new graphical user interface, new 3D rendering of the geometry in the graphics window of CAESES, a new so-called app view, about which we will learn a bit more later on, some smaller changes that make the modeling process easier and also allow to create cleaner project structures, a new multi-threaded core inside of CAESES, a new design space dimensionality reduction method. Again, this might need a bit more explanations later on. New morphing methods for imported geometries, improved documentation to make starting with CAESES but also looking up things easier, easier access to support to get in contact with us, and easier license administration. So let's start with the first topic, the graphical user interface. This is definitely the first thing you will see when you open the new release. The new user interface is more organized, it's easier to use, it also has a more modern look, which is, let's say, nice to look at, but I think the 2 points at the beginning are very important, which will ease the process for existing CAESES users, but also new CAESES users. And this new user interface introduces the concept of workspaces, which means complete arrangements of windows and menus that are dedicated to specific tasks, so that it's easier to find the functionality that you need in a specific task. It brings along things like ribbon menus, which I think is a familiar element. A new design and icon set. There is a light and dark style to match all preferences. And if you have preferences that go beyond what is readily available in the user interface, it's also fully configurable, so everything can be adjusted and adapted based on your requirements. What you also see in the user interface in the graphics window is the new rendering engine. So we have introduced a new, more advanced rendering in CAESES 5, which allows a more realistic view on your geometry models with more realistic shadows, transparency. You can set at least visual material settings to your geometry, which means how reflective it is, how shiny it is, things like that. You can place your model in 3D environments, and which wasn't available before. We also can set local global settings for things like render accuracy or specific views like section view and isophones. And also the performance has increased, so we have a much higher rendering speeds, especially for large models, imported geometries with a lot of small patches, things like that. Everything is much faster and more fluid. And also this rendering engine is a necessary foundation for new developments that regard interactive working in the 3D view. We will see that later on in the new morphing capabilities in CAESES 5. The so-called app view is a new view. It's a simplified view on a project setup, which can be configured by an experienced CAESES user, for example, to share complex projects and workflows with his colleagues that might be less experienced or don't have any CAESES experience. It can be used directly within the CAESES interface or via a web browser, both locally in the company network or remotely. And there are many different elements available to configure this app view that can be connected to parameter values in the CAESES project, sliders to set values, fields to look at values, buttons, things like that. And the last topic for what we see at the surface of CAESES is some improvements for easier modeling and cleaner projects. We have introduced so-called dynamic object types, where you can simply create a curve without specifying directly which type of curve you want to create, or a point or a surface, and then you choose the creation method after you have generated the object based on a certain task that you want to do with this object. And you can also change this creation method later on in your project without breaking the dependencies. Another improvement are post-processing operations at the object level, so you can directly modify objects without the need for image or transformation objects. This is something existing CAESES users might be familiar with. And this speeds up the workflow, and because you have less additional objects, it keeps the project structure slim and clean. And finally, improved object tree search, where you can search for objects and filter your object tree so that it makes it easier to find specific things or have certain views on your object tree with only certain types of object that you want to see. Again, this is what the first things you will see on the surface, a short overview, and now I will give over to my colleague Carsten, who will give you a live demo and show these things in real life in CAESES.
So, hello. Hello, everybody. I hope you can see this new CAESES
Yes.
interface here. In today's presentation, I not only want to show you all the details of the new interface, but I also want you to tell you a little bit the story behind the scenes of how we did how we did that and why we actually did that. Because our goal was not to just came up with a new polished modern like design or something like that, but we really wanted to improve the workflow for advanced users, but also for new users. As you know, CAESES has a lot of different object types, let's say, for points and curves and surfaces, which really makes the parametric shape design smart and powerful. But there was always the challenge to organize all these objects in an efficient way. So we thought about new ways of distributing all these objects to the user, and yeah, we finally came up with the let's say ribbon graphical element, which you can see here at the top. I think most of you know that, and I think it's quite controversially discussed by different users with different softwares, but we really felt that this is a really good way inside CAESES to organize all these things. So you can see we have now here a ribbon where you can find points, curves, surfaces, and so on. And these are also then grouped by point-based like groups for points, for curves, and surfaces. So it's quite easy now. Let's say you want to create an offset curve. So you would think of, oh, what is an offset curve? Okay, it's a curve based on another curve. So we would look for a curve-based curve, and you can find here the offset curve. So that makes perfectly sense and is, yeah, more organized now. But of course, the ribbon is also some kind of limited, that you cannot like fit all too much objects into the ribbon, and that's why we came up with the tabs, which you can see at the top. So we can basically group the objects for different tasks. Like we can have now a tab for feature definitions, for turbo machinery applications, for maritime applications, for visualization, and so on. And another great thing with the tabs is basically that not only the ribbon changes with the objects you can create, but you can also see that the, for instance, the object tree changes, that you are having new options in that ribbon. And also we can display different windows and so on in that tab. But when we implemented all these ribbons and tabs, then we certainly at a point realized, okay, that we cannot have too many tabs here at the top, because it's also quite not organized well. So we had to find a way to group certain tabs. And we came up basically with the idea of workspaces. So what is a workspace? You can see them here on the left sidebar now. So we can group different tabs into one workspace. For instance, for model, you have a workspace for connection, for optimization, and so on. So it's easy accessible, and in each workspace, we have different tabs. Let's have a look at the workspace connect. So we have, for instance, here the connection tab, where we have the software connector included. And then we have a post-processing tab, where we can have a look at the results of our object. So you can see this is some post-processing result of that duct I showed you. You can here now have access to all kind of different things. Maybe you want to have a funky color map here. And you can also see, you can switch to different designs which you might have created already. So maybe I can jump into one of these designs, and we can see then how the post-processing results updated. We can see now here in green highlighted that we are in design 006 now. Okay, just a detail. Let's go back to the baseline. Right, and have a look at the optimization workspace. So in the optimization workspace, we just have one tab, which you can see here, optimization right now. And the ribbon is basically groups with general constraints, and then some design engines for design space explorations, like Zobo, Latin hypercube sampling, and so on. Single objective optimization, multi-objective optimization, and further design space utilities. And yeah, in the tree, you see the design engines and also the different designs. On the right-hand side, you can see if you have run a study, you can see some designs. You can have a look at the design viewer, compare different designs, look at the 3D view, and so on. And of course, we also still have the old functionality of the charts to compare design variables and parameters. All right, and then let's have a look at some other workspaces. You can find here the app view. I will go to this a little bit later, but now you can also see the help workspace, where we can find the cases documentation, cases tutorials, and cases samples, and so on. So it's a good way if you have any questions to look first here. All right. But this is basically the graphical user interface, but let me show you a little bit more exciting features, which basically makes the modeling easier and also the projects better organized. So we came up, let me switch off the filter here and hide that. So we came up with so-called dynamic types for points, curves, surfaces, and you can find them here at the top of each category. So let's say we have here a dynamic curve, and by default, it's an empty curve, and you have to create set a creation method. For instance, you can create it with a line. Then you see you have the line. Then you can switch the line to maybe an F-spline, where you can change the tangency, let's say, of that line. All right, so let's have a look at the real model, because that is quite nice when you have a complex parametric model. Let's say you have this duct shape here. This duct shape is based basically on that center line, and it's parameterized like with an angle, with a tangent factor, and so on. And at a certain point in your design, you realize, okay, maybe this is not the perfect definition of that curve, so you want to have a different one. So as an example, I created here already a few points, and you maybe want to change from that planar curve with tangent control to a maybe NURBS curve. So that's quite simple. So you can just go here and change to NURBS curve, for instance, and then let's drag and drop all these points into the list. All right, so you can see now the whole model updated. You have now complete control of that new curve. Really flexible, and all the dependencies which belong to centerline are kept. So it's quite nice. Let me go back in history just to remove that step. Maybe here. So you can see I just have now the planar curve with tangent control again. And another exciting feature which we have is we have post-processing operations directly on the curve object and surface and so on. For instance, if you want to trim the curve by a certain angle, you can just go ahead here, go to trimming, and then maybe trim by tangent angle. You can set maybe to 45 degree, and then you have to activate this post-processing operation. You can see it's now trimmed at 45 degree. Maybe you want to trim it at 60 degree. Maybe then you decide, okay, you want to extend that curve, right? So let's extend it by 50%, activate it, and here we go. So we extended that. And maybe then at the end, you want to rotate all this stuff, maybe around the z-axis, maybe by 30 degrees. So I can see now it's rotated by 30 degrees. So really nice kind of operation chain here in the post-processing operations. And we didn't create any extra objects, so that keeps your project really organized. All right. So let's just remove that. All right. Another exciting feature is the rendering in CAESES 5. So right now you can see it in the 3D view, and we can change the settings of the rendering by clicking here in the 3D view on that icon here. And you can choose a different environment. So let's say we can have a look at the environment multi-area light, and we can show also the environment with that button. So when we twist it, that is basically the environment, which basically then reflects on the geometry. Let me switch that off, and then you can choose the material properties of that object. So you can put it to the roughness, let's say to 0, then you can see it's a really shiny metallic look, and you can increase the roughness to have a more like realistic look. And another nice feature is to visualize the isofolds of the design to see if there is good tangency between different patches. All right. The last thing I want to show you is the web application, or the app view, which is called inside CAESES. So it's quite easy in that version now to set it actually up. So we can go, let's say, to the design variable overview, and you can find that button here on the right, which will create basically the web app page for that overview, basically for all these design variables. So let's click on that. We create the page of that. Then we go to the app view. We go here, and we can find the page which we created, and we see also the web apps. So we can create different web apps with different pages and so on. So let's publish that one. And here we go. We have the web app, the app view, which we can change here, let's say. And then just as a small demonstration, maybe you can easily add, for instance, another object here. Let's add a button, for example. Then we go here to add new operation, create a new standard button here. So let's call that button export, and we want to export this geometry in step format maybe. So let's look for the object BREP. Therefore, I use our object tree filtering. So it's quite easy to, let's say, find the BREP object. I just write here BREP, and then I can put that BREP object here, and then I write the command export step. All right, so that will basically export that type in step format. So now we go back to the web app, click on publish. We can see the button here. We can go into full web app view and then click here on export, and then it will basically export the pipe in step format. Okay, that's all from my side.
Great. Thank you very much, Carsten, for this nice demonstration. So let me take over again and quickly talk about the next topics. So as I mentioned before, what Carsten showed now are the things at the surface of CAESES, and but also something at the core of CAESES happened, which actually was the main driver of the development of CAESES 5 over the last several years, which was a complete re-implementation of the core of CAESES to a multi-threaded application. So now everything is fully parallelized and supports multi-core processors. So before, CAESES only ran on one of your processor cores, which in an optimization process, the update times for the geometry variants are negligible in comparison to CFD runs. But if you're working on your model and you're doing some interactive work, sometimes it's annoying to work to wait for the model to update. And that has become much better now. And also an additional point is that the update now happens asynchronously, which means the interface will not freeze or become unresponsive when the update is happening, but you can actually change, for example, a parameter value, and then while the geometry is updating in the background, you can continue to work, change other parameter values, for example, or do other things. So you don't need to wait every time if you have a very complex model that can take a long time, and that's quite annoying if you want to do several steps one after the other. And we can see this here in this demonstration in comparison. So we have the CAESES 4 on here on the left side, CAESES 5 on the right. We have changed the same parameter value for the same model, and you can see the update is now running on both systems, and now CAESES 5 has finished updating already, and here additional parameters are changed, and you can see they're changed one after the other without waiting for the geometry to do the final update. While CAESES 4 is still working on that update, we're still waiting. In CAESES 5 here, we can continue to work, rotate the model, change views, select objects, things like that. Still waiting. Of course, not all the updates in CAESES 4 were so long. This is a particularly complex model that we picked out, and you can see after 57 seconds the update has finished. So I think very good improvement, especially for heavy users of CAESES that work on complex things. And while we're talking about speed, another issue is speed of optimizations. So often our customers are working with parametric models that have a high number of free design variables, which would require many simulation runs to get an idea of for example, of the design space, which can be quite expensive if you have expensive individual runs. So we introduced a new methodology here, which is called design space dimensionality reduction in CAESES 5, which is based on, some people might know this, principal component analysis. And the idea behind this is that we transform the parameterization of our current model to a completely new parameter space. And when we're doing this, we remove correlations between the parameters at the same time. So what we mean by this is often in your parametric model, you have certain areas of the geometry that are influenced by several of the parameters, because let's say the areas of influence are the same or overlap at least between the parameters. So you have some correlation between your parameters this is normal, and this is what we're trying to reduce to really boil down the parametric model to a new set of parameters that are completely uncorrelated. And this brings along a massive reduction of the number of the free variables while keeping the variability or flexibility of the model constant, basically, or at a similar level, and which would then lead to a significant speed up of the optimization process. So you can find this in these design space utilities and the optimization ribbon, as Carsten has shown before. This functionality is currently available for all users for testing, so feel free to take a look, test this, give us your feedback. Later on, it might move into a dedicated package, either in the advanced optimization package, if people are familiar with that, or in other packages. But currently we decided to make it available to everyone, so you can have a look and try it, even if you don't have this dedicated license. So how does it work? From the process, you start building a parametric model as usual. We have again a duct here. Then you produce a large ensemble of variants with the design of experiments algorithm. So you have your geometry variation, many different variants. And as you can see, if we look at this animation here on the side, it looks a little bit like a complex vibration of the geometry. And at least to me, I think a good visualization of this method is how you approach vibration phenomena, where you break down the complex vibration shapes into eigenmodes. And this is similar here. You have a complex variation of the geometry and you break it down into so-called principal components. And here you can see for this duct the first 4 principal components. These are the modes of variation. These are extracted from this pool of variants. And now we can choose how many of these principal components we want to use. These are, so to say, the new parameters for the model in the new parameter space. And then we can start optimizing with these new parameters. So the optimization algorithm, rather than changing the values of the original parameters, can change the values of these principal components. And once we have a combination of values, we can transform that back into the original CAD space, set the parameter values accordingly, create the geometry, analyze it, and give the feedback to the optimizer. And then the optimizer can create a new variant based on these principal components. And you can see here that it's quite easy to reduce the number of parameters quite massively. For this duct example, if we use only the first principal component, we retain slightly more than 50% of the variability of the original model. And already if we add the second principal component, we cross 90% of the original variability. And the more we add, of course, the more we come closer, but we don't need many to have a variability that is really close to the original model. So we're not missing out a lot of the original design space, but we have a much smaller number of parameters. Yeah, and before we talk about morphing, I would like to invite my colleague Heidi to give you a small demonstration of this design space dimensionality reduction method.
Yes, thank you for the introduction, Mattia, and the first explanation of the dimensionality reduction. I would like to show you now here a little bit how the images Mattia just showed you and the dimensionality reduction was set up to explain this a little bit more in detail. So we have a duct example here that's quite a simple one with different cross sections as a meta surface defined here. You can see some cross sections going from a circular shape here at the inlet to a more like a rectangular shape at the outlet. And then we have set up in total 14 different design variables, as usual, as a parametric model that define the shape of our duct here, which is the one we would like to use for our example case here, but running an optimization with all those 14 would be quite cost intensive and resource intensive also. So that's why we used this to try the dimensionality reduction and actually try to set up a meta model that could find the design variables or detect the ones that influence certain parts of the geometry maybe in a similar way and get rid of those correlations. So in order to use the dimensionality reduction method, it's actually located, as Mattia has shown before, here in the optimization workspace. It's not an optimization algorithm itself, but rather like a supplementary tool that can be used before starting the optimization. So if we create a dimensionality reduction model here, or want to create this meta model, we actually need to define a number of variants that we want to create in order to put together the geometry pool where the original 14 design variables in this case are modified and where we want to detect the correlations here. So let's just put 200 variants, and then for this example here, maybe go with like 300 sample discretization points we want to put on our geometry. Then we choose the geometry we want to look at. In this case, we pick the duct, the surface wall, and then we need to find the design variables that we would like to use here, that we would like to modify in order to derive the model. So let's just pick the design variables here and put them into our dimensionality reduction object here. So we want to create the model with those 14 design variables. And then let it run so that the model can be created. Let's do this. This usually only takes a couple of minutes for those, or in this case, maybe just about a minute to create those 200 sample models. You can see here that the path is varied in a way to, well, we don't see the other functions that are also varied by all those design variables here in order to get the derived model. So this is just the preparation to use the dimensionality reduction, which we will later put into maybe a design of experiments here, use a SOBOL that will be based on this dimensionality reduction and will use not those 14 design variables, but rather the new principal parameters that will be derived from here. So if we look at this, now we can see the black shape here. That's our so-called like a meta model, our new maybe discretized shape with the number of 300 sample points we typed in earlier. And if we go here and set a number of principal parameters, let's say we want to use 4 in our optimization, we can see that, well, okay, this is quite good already. We have 69% of the flexibility, the original variance and variability captured here. So if we want to look at the influence of each principal parameter that is happening, I can move those sliders here and see what kind of modification is done and applied to my dimensionality reduced shape here that will drive my optimization algorithm later on. If I want to get kind of a more detailed look, or those sensitivity contour plots on my geometry, or shown as a vector here, I can use the sensitivities down here, see on my geometry what region is most influenced by which principal parameter, what is happening if I move the third principal parameter, for example, just to get an appreciation and an overview of what can be done and what is modified with these principal parameters that were newly found here. So the black shape is our meta model, our dimensionality reduced model, but what we're most interested in is that we find those original design variable values for the shape that will be defined by those principal parameters here. So that's why usually, as Mattia mentioned already, the back transformation comes into place, which is what happens each time that a new shape is defined with those principal parameters. Actually, each time the original design variable values need to be found so that actually my NURBS-based model, my original model, tries to match the shape defined by the principal parameters as good as possible. So this step is what happens each time. I just triggered it manually, but if we put it into a optimization or exploration algorithm up here, this step is what happens at the end of each shape variant creation with the principal parameters. So if I want to use this now, maybe in a SOBOL, and run a design of experiments, I can choose my meta model, my dimensionality reduction model here, put it in and see, okay, I have chosen 4 principal parameters here with 96% of the variance retained, and I want to run a SOBOL base, or let's just run 10 variants here. This is just from a pure geometrical view, so we don't have to run any CFD or anything else. We just we can add some evaluations to it, of course, which I won't do right now due to the time. And also we can add some design variables, but those aren't the original ones that are only being monitored in this case. So they appear in the design result table. Because those are the ones that are dependent from the values that are decided for each variant from our principal parameters. Of course, let's just create 10 variants here and see what shapes are created. So the actual shape is defined by those principal parameters, and then a back transformation happens to find the NURBS-based original BREP model, which we can see in the screenshots I'll show you in a second. Okay, so this has finished. Let's see here. So we can actually see that those variants have been created and the back transformation has been transformed. Running more sample variants in the beginning of actually setting up the meta model helps in increasing the accuracy of the back transformation. But this is usually a nice way to actually explore a design space by only using 4 principal parameters in this case, instead of using the 14 original ones. And this can actually help save optimization time and be really beneficial in the first phase, especially when you want to find a subspace that is, or like a tendency in the design space where good results are very likely to be found. So as Mattia mentioned, yeah, we would like to encourage you to test this yourself, give us some feedback and help us improve this a little bit more. Thank you.
Great, thank you very much, Heidi. Really great method for, as I mentioned, complex models with many parameters to do a quick optimization or a quick scan of the design space with a much lower number of parameters. This is actually the topic that Hedi did her master's thesis on, as I mentioned before. So really interesting. So the next topic and the next new functionality in CAESES 5 that I would like to introduce is morphing. As you might be familiar with, we always had some kind of so-called morphing methods in CAESES, or what we also used to call them partially parametric modeling. So many of our customers are actually working with so-called fully parametric models, which means you create a model, a geometry model from scratch within CAESES and define all your parameters as you go along. But quite often you also have a case where you have an existing geometry that comes from another CAD system maybe, and you would just like to do a quick optimization on it and do some modifications to this imported geometry, and that's where partially parametric modeling or morphing comes into effect. As I said, we had some methods for doing this before, but we wanted to increase the capabilities of CAESES for this approach because we can see there is quite a certain, let's say, group of customers that can work very efficiently with this approach. That's why we introduced new morphing methods now in CAESES 5, which are based on radial basis functions. And the first of these is a interactive morphing where you define your deformations to the geometry interactively with a paint tool, decide in which area you want to modify, you push and pull your geometry, as you can see in the animation. And this works only currently, at least, on discrete geometry, which means something like an imported STL file or a mesh of some sort, surface mesh. And then we have also another method where the deformation is based on a source and target geometry. Like you see in the animation below, we have a source curve in this case, which is the feature line at the end of the roof of this vehicle, and then we have created a new curve, the green one, which is the target, and then the geometry. This is used, so to say, to compute the morphing deformation to go from the original source geometry to the target geometry, and you can also use interpolate between these two or extrapolate in both directions to create new shapes. And this really gives an easier and much more flexible approach to parametric variation of imported geometries than what we had before in CAESES. Of course, the other methods are still available in CAESES, but these here really add a lot of new flexibility and speed in defining these parametric variations. And now I would like to invite Heinrich to give us also a small live demonstration of this functionality.
Thanks, Mattia. I think there's a common misconception about whether partial or fully parametric modeling is actually the way to go forward. People often feel like they are at some sort of crossroads where they have to choose whether they want to go for a fully parametric model that offers them all the freedom and all the complexity of the design space, or rather go for a partial parametric model where they would modify some imported or maybe geometry that is derived from a different model that they already have. And the truth is, in most cases at least, that these two are actually used best in conjunction. So it's not like there are two different roads to go down, but it's rather like two different directions. You can think of it as two different vectors that span a plane, and to reach any point in that plane, except for the axes themselves, you need to combine both of the techniques together. And now what we have done with the morphing in CAESES 5 is actually opened up some sort of a middle way. If you will, it's you can think of this as some sort of a shortcut, as it overcomes certain flaws and drawbacks that we have had with the old traditional freeform deformations or shifts and all these partial parametric modelings, and allows you to do, based upon existing geometries, things that were previously reserved only for fully parametric modeling approaches. So I've brought along here an example of a ship hull. This is in fact an export from a fully parametric model re-imported into this project file. So just to underline what I was just stating, and I've put together here a couple of transformations. I've shown a similar example in a webinar we just did a week ago in the framework of Holy Ship together with Kongsberg. I just want to really quick go through the modifications that we've put into place here. Let's start by looking at the bulbous bow, maybe, where we can change through a freeform deformation the thickness of this bulb here. So like so. So we can change the thickness, make it way narrower or a lot wider if we wanted to. We look directly from the front, we can shift volume up, and we can also bring it down, or we can change the length of the bulbous bow. In this case, a delta shift is used to modify the shape. We can move it up and down. In this case, it's a delta product to ensure that the deck stays horizontal while we move the bulb itself up and down here. And then what's also put in place is a slight variation of the forward shoulder, because usually if you do this kind of modification, you're looking at the wave resistance of a ship. So if you change the bulb, you maybe want to modify the forward shoulder as well to find a favorable interference of your waves that you generate to reduce resistance. So I can make this fuller or more slender with a surface delta shift in this case. And then I can do even large modifications, like changing the dead rise angle, moving up the flat of bottom here to an angle, or tilting in the sides by introducing a flare angle. What all of these, let's say, traditional methods of partial parametric modeling have in common is that they are not distinct. So in many cases, you can specify what you want to do. Let's say we talk about the thickness of the bulb. We can make it wider or narrower, but we cannot define a distinct outline. So, and that is sometimes what you want to do. Maybe you want to set a certain waterline shape to your model, or you want to set a certain contour to the bulbous bow, because you just need that for some reason, because you have constraints or because you have empirical data on the waterline entrance angle that you want to make use of. And these kind of things were in the past often reserved to fully parametric modeling, where you could use meter surfaces and ensure that certain shapes and sections would be matched. But now with the B-rep morphing, what we can actually do is do just this on existing imported geometry. So if we look at this here, what I've done is I've created myself this little curve, which keeps the tangent and curvature of the original stern valley here, and it's controlled by this point. So I can move this point around in space freely and change the shape. And then I can use B-rep morphing to conform my existing geometry and make it match exactly that new shape. So if I turn this on here, you can see that we perfectly match the new given tunnel geometry. And what I can also do is I can interpolate somewhere in between. So instead of just turning this on and off, I can go to somewhere like 0.5 and have a new geometry that is right in the middle of the two existing variants. And I can even extrapolate to maybe 150% here. And I could also go down to negative values, in fact, if I wanted to. Like so. I've created another example at the knuckle line of this ship. This is quite a common topology. For some ships, you would see a sharp knuckle here. For this one, it's smooth, but still similar to what I explained earlier about the interference of the bulb variation and the forward shoulder. This is a very interesting area when you're looking at not just resistance, but maybe even hydrostatics. And in resistance, it's also maybe not just wave making, but frictional resistance, because you have a lot of area to tweak here. So what I did is I created myself two curves. One, as you can see here, let me turn this off real quick. It's the green one. It's just a copy of the current shape. So I've taken from our last modification this knuckle line, created myself a copy, and then I've created basically a copy of that copy, which I am able to put some modifications to. So the blue one is my modified geometry, and I can control this with the design variable dy here, which allows me to shift that endpoint left and right. And I have another one, dz, which allows me to bring it up and down. And then if we look at this object here, that's the BREF morph object itself. It doesn't need a lot. It takes in the latest geometry variant, which in this case comes from this folder number 10. It needs a number of morphable faces. So if we look at this again, the 15, 14, and 9, that's actually this, and that patch of the BREF. So these are the ones I want to modify. We can also take a look at the fixed points. Over here, you can see that I have 3 rows of control points so that I can fix the contour in space and tangent and curvature continuity. And then I can specify my source and target. And these could be points, could be curves, could be surfaces, whatever it is. And as soon as I enable that, you can see that my BREF immediately, let me turn off the fixed points again, conforms to the blue curve that I've freely chosen. And it perfectly matches it, and it keeps the continuity towards the rest of the shape. And then, like Mattia mentioned, we have taken this one step further just to open it up for a broader range of applications, and also implemented the same functionality for tessellated geometry. So say you have an STL file that you have imported, and then let's maybe pretend that there is some sort of deck given here. Maybe we need to fit a certain number of car lanes or a ramp for boarding and unboarding of the vessel here. So what I've done is I've taken a tri-mesh as a copy of my hull. I've intersected it with this deck surface here to get my source curve again. So this is the initial source curve. And then I've created again a new variable curve, which is called target over here. And I can control this target curve, for example, with the entrance angle over here. So I can make it fuller. Also this area factor, which can make it narrower and wider while keeping the given tangents. And then all I need to do is create myself a mesh morphing object that takes in this tri-mesh hull as an input. So I click on apply here, and I can hide my existing hull. And then I need to add a new region, a region into which I want to apply my deformation. This vector handle method is what Mattia has just shown in his presentation. There's also generic transformations available. And like I said, I'm going to use these source and target curves here. So just put them there and select to edit my region. And I can very conveniently here paint the region that I want to actually apply my modification to, just like so. And as soon as I finish editing, you can see the geometry conforms to my newly given blue curve. And if I were now to change the entrance angle, for example, here, you can see that it follows along. And that's it from my side. And I would hand the presentation back to Mattia for our final Q&A session.
Great. Thank you very much, Heinrich. Let me switch back to my screen. I have just a few last minor points to mention. The documentation has been improved in CAESES 5. Carsten already showed you the documentation workspace and help workspace with the documentation page where you can find the access to all the different resources. One other thing to point out is that we have improved quite a lot the search function. So now if you're looking for certain keywords and you want to find articles, material, information about that, it's works much better. It's much easier to find. And then if you don't find what you need in documentation or you have something to report to us, you can use our help desk, and we introduced a new help desk a little while back already, and now this help desk can be accessed directly within the user interface of CAESES. And what is Especially interesting, I think, is that you can create a help desk ticket directly from the user interface. So if you encounter a certain problem or you have a question, you can create a ticket here from this button, and you can directly include a screenshot of the user interface, of the current user interface of CAESES, and you can also attach the project file that you have currently open, and that makes it really easy to create a ticket. You don't have to go to your browser, open the help desk, create a new ticket, and so on, but it's really much faster. Okay, so much for the news. I think we are slightly over time already, but we have a little bit of time left for questions. If there are any questions, let me take a look. There is one question here. Actually, this may be something for Heidi, which is, what is the error tolerance between the dimensionality reduction and the original model? Sorry, you are muted. Let me just unmute you, Heidi, and also the other ones. Yeah, the difference basically between the dimensionality reduction model and the original model.
Well, that kind of depends on how good the model is and how many variants have been created in order to feed that geometry pool. We don't have like a really, like, I'm not familiar with the tolerance number we have there, but the back transformation does get better with more variants you feed into it in the beginning.
Yeah, and I think it makes sense. As far as I know, basically to do the back transformation, we do an interpolation of sorts between the different variants and parameter combinations that were used initially to create the model. So that would make sense. Maybe a quick question here. I think I know the answer, but if you have any input, let me know. Are projects created in older versions completely compatible with CAESES 5? I think so. I think we typically take a close look at backwards compatibility, and I think everything that has been modeled and so on in CAESES 4, we should be able to open in CAESES 5. Are there any things maybe that you know of where maybe one would have to be careful?
Oh, the
maybe
only thing.
Yep.
Sorry, Carsten, go first.
Carsten, maybe.
Yeah, maybe just maybe it's not that obvious, but obviously you cannot open CAESES 5 projects in CAESES 4. So this is just one thing you have to be careful.
Yeah.
Not to start like a really large project and then you realize you are at a certain point you have to go back to CAESES 4, something like that. That does not work. But actually most of the things will work. There are some graphical elements like 3D diagrams and so on, which might be not working at the moment, but at least geometry-wise, from my knowledge, everything should work.
Yeah, thank you very much. Maybe also one thing to point out here, the file format for the project files has changed. So now in CAESES 5 we have the file extension is CDB. So previously we had FDB with CAESES 4. So when you open a CAESES 4 project in CAESES 5, actually a copy in the new format is created. So you will retain your old project in FDB format, and the new copy in CDB format will be saved. So that's also as a backup, basically, when you change from 4 to 5. And that's also the reason why that it's not compatible in the other direction. This is a basically new format, and you cannot open these files in CAESES 4. maybe let me take a look. At some
Maybe while
questions.
Mattia goes through the questions, I would like to add that there's also a very few commands that have changed between 4 and 5. That isn't to say that these things are not available anymore, but if you experience problems, say in feature definitions that you used to use in cases 4, which give you some errors in cases 5, and you're not able to fix them by yourself, feel free to get in touch with us. Also with any other issues, like Matthias said,
Yes.
we keep a close eye on this compatibility. So if you have a project that worked for you in 4 and doesn't open in 5, feel free to get in touch with us. Besides these small things that Carsten mentioned that we want to add in the near future anyways, things should basically work in between these two.
Yes, very good. I have a question here about the morphing, the RBF-based morphing with the source and target geometries. The question was, what kind of objects can I use for sources and targets? You've shown curves, I think, throughout your presentation. What are other options to use as input for source and target?
Yeah, I might have missed to mention that, but basically what you can use in the BREP morph is points and curves and surfaces. And in the mesh morphing, I think it's curves so far. While in the mesh morphing, you also have additionally the functionality of placing these vector handles that Mattia has shown in his animation. And what's also interesting to know is that you can't have just one source and one target. You can have any number of sources and targets, and they are then those two lists need to be in order. So you can have 10 points mapped onto a second list of 10 other points, and then point 1 will match point 1 and point 2, and so forth.
Can you also mix the types of source and target? So you, for example, you have one point source and target and one curve point and target in the same list?
I guess so, yes.
Sure, yes, it's possible.
Okay, great. There is a question here. I don't know if you have the answer. I'll still pose it about the multi-threading capability. And the question here is, does the user need to assign the number of CPU cores, or is it automatically recognized? Do you know that? If you
I think there's a way to start up with a given or assigned number of CPU cores, especially when you're in cases in batch mode. But as far as normal usage is concerned, just start it up and use this as you would use any other tool on your computer.
Yeah, and then basically it uses all the available cores,
exactly.
balancing loads as it does. Okay, that's good. Oh, this is one question which goes maybe to Carsten. I think it touches on the configurability of the user interface. One user here says, one thing I miss from case 4 is the set of icons in the middle of the screen. I think this was the so-called create toolbar in the middle. Carsten, I think it's possible to bring it back, right, if you really need this.
Yes, so we can bring it back. It's also available right now, but we have to. Okay, I have to find a diplomatic answer.
Maybe you have to really think about if you really need it or not, because I guess these things that are and were in this toolbar are also available in the new menus now in a more sorted way, maybe. So maybe it's a question if it is really necessary or not. But yes, maybe the overall answer is you can configure everything. As I mentioned before, you can also get rid of the ribbon menus at the top, and you can only activate this toolbar as in the old version, and so on. So everything is possible. yeah, I think maybe it's up to every user to get an impression of how things are now and whether they can work or maybe even work better with how things are now, or if they want to go back to some of the old ways, let's say.
Yeah, I think in the future we also make it possible to set up own toolbars and with own, let's say, objects and so on and menus. This is right now not really possible, but we will also work on that so that everything is a little bit more customizable by the user.
Mm-hmm. Okay, great. So I think that's all the time we have for today. It's 1/4 so I'm gonna finish up this webinar now. Just a few hints what to do next. Of course, if you haven't done so already, and some might have done already, you can download CAESES 5 on our website on the download page in the different versions for Windows and Linux. If you are not an existing user and are not able to use CAESES with an existing license, then of course you can register for a trial license after the installation of CAESES. And otherwise, watch out for more webinars coming soon. As I said, there might be additional, more in-depth webinars about some of the new functionalities. And of course, we also have other types of webinars, so you can take a look at the event section on our website to find announcements for new events. And if you have any questions, problems, either use the help desk as I showed before, or for more general questions, you can contact us at info@friendshipsystems.com. Thank you very much for joining. Stay safe, stay healthy, and yeah, I hope to hear from you or see you soon. And for today, thank you and goodbye.